welcome back. This is lecture for, February 18th. All right. Hopefully your week has gone well so far. We're going to pick up kind of where we were in the last lecture, which was talking about columns, right? These long, slender, prismatic members, right, that have this phenomenon of buckling that can occur where we get this sudden large deformation of a structure due to a slight increase of an existing load. So it looks safe, we increase load a little bit, and finally we just get to this breaking point where it will lose all load carrying capacity and essentially collapse, right? And we get a large deformation. So a very undesirable failure mode for structures and elements, right, and designs. And so we better understand the behavior and be able to predict the capacity. And so we do that based on Euler, okay, and his developed equation for this ideal pin-pin column. Okay, and it gives us this equation which then we were able to relate back to different boundary conditions of our columns, right? If our column was pin-pinned or fixed-pinned or fixed-fixed or what have you, we are able to then calculate our capacity, whether it is a axial capacity P critical or an axial stress, right? Capacity stress, which would be sigma critical, all right? And as we know, based on the parameters of our equations, right, we're going to have some radius of gyration, which can be a function of the slenderness. And fortunately for us as engineers, don't want to redo things, right? There's standardized shapes, especially in the steel and metals industries. Okay, I'm sure METs know this already, but there's a lot of standard shapes out there. So for instance, on the CET side in building construction, all right, this is a page out of the Appendix B, and it is all about a standard American channel, or what you would call a C shape, right? So we have our C, which denotes it is a channel. 15 is our nominal depth, okay? Nominal meaning that all of the C15s have a depth that is close to or at 15 inches, okay? We also have at the end of this designation, in this case for a C15 by 50, well, that is our weight in pounds per foot, okay? So if we had a 1 foot piece of a C15 by 50, we would have a 50-pound piece of metal, okay? And as you can see, as we work around here, it gives us all sorts of dimensional information, right? Which is laid out in this diagram at the top of the page, which tells us what the flange width is, right? B sub F, flange thickness, web thickness, the centroid of the section, and most importantly, right, all of these parameters here, which we can utilize as designers, right? The moment of inertia, which obviously for a C section like this would be fairly complicated. We have very, not super complex, but complex enough geometry that it would be a pain in the ass, right, to go through and calculate what our moment of inertia is. And so we have tableized values for that. So we can go online in the text in D2L, right, and grab out of the appendices, and you can go out there and pick up what essentially a sheet that associates with a given section. And there's all different types of sections, but this is just an example of a C shape or a channel, okay? Well, if we do an example here, we have two C12 by 25s, okay? So its nominal depth of these channels is 12 inches and the weight per foot is 25 pounds per foot. We can look in Appendix B for some cross-sectional properties, which we will in a second. It's used as a 30-foot long column, okay? And we can assume that the column is pinned at both ends, okay? And we can use a modulus elasticity of 29 thousandths because it's made out of steel. And we want to determine the total compressive load required to buckle the two members if, and we've got two conditions. One is if they act independently of each other, or if they are latticed back to back as shown, right? So in one condition, we are going to look at it as if these blue members didn't exist, and then we're going to look at it as if they did, right? So in one case, we wouldn't have these members there. It'd be just having two channels spanning our 35-foot tall height, or right? We might have those blue members in there, which essentially makes this a uniform section, and that's going to affect our capacity. So if we go to Appendix B first, we start out this problem by figuring out, well, what are our cross-sectional properties of interest? Well, we know we're going to want to know the area. Well, we know the area based on, right? We just go to this sheet, and obviously I happen to set this up so that this is the sheet that we looked at previously. We know that we have a 12 by 25. So all of the parameters that we need, we can just merely grab out of that row of Appendix B. So the area is 7.34. The centroid is at 0.674 inches. We have a moment of inertia about the y-axis of 4.45 inches to the fourth. We have a moment of inertia about the x-axis of 144 inches to the fourth. Okay, the length of our column we were told was 35 feet. We might have to manipulate some units there. As you can tell, everything else seems to be in inches. Okay, we have a modulus of elasticity of 29,000. Okay, that is standard for steel. I'm sure a lot of you will devote that to memory as you guys continue through academia and into your careers. And then finally, we know that in our stress equations, right, and our capacity equations, we have this effective length factor. We call it K. And in this case, if we have a pin column, which they mentioned to us, we have that initial factor of 1, because that was the original solution that Euler had to this problem is 1. Okay, well, if we're looking for the compressive load, right, we're looking for P critical, not sigma critical. And if we go back and look at P critical, well, that's pi squared EI all over KL squared, right? Well, if we look at part A, we're looking for the total compressive load required to buckle the two members. Well, if they act independently of each other, we truly have just two of them. Okay, so the P critical total really equals P critical of one channel, right, times 2. Okay. Well, as we know from our previous review here, as we started talking about this buckling, well, this buckling, right, can happen in two directions, right? We could buckle, say in this cross section, we could buckle it one way, or we could buckle it another way. If we were looking at this square cross section, right, the square cross section might buckle to the right, or it might buckle upward on the page, right? So similarly, we've got these channels, okay? We're gonna want to look, right? We have two axes to look at, right? We have X and we have Y, right? This might be our Y-axis. This might be our X-axis, right? So effectively, these channels could move side to side, right? When it buckled, it might look like something like this, right? Where it buckles to the side. Or it could buckle the other way, right? It could buckle in the Y direction. So with that being the case, let's look at the X direction, okay? So that'd be the buckling about the X-axis. So if we look at buckling about the X-axis, right? So that would be, if we were buckling about the X-axis, that would mean we would rotate about the X-axis. That would mean that our cross-section is really traveling along the Y-axis, right? It would buckle upward or downward, right? But it's rotating about the X-axis, because if we looked at it from the side, okay, it would look something like this deflected shape, right? It's going to buckle in the Y direction if we were looking at the side of that, okay? So get rid of that. So let's look at the critical buckling load of buckling about the X-axis, right? So rotating about the X-axis or moving, right, in the Y direction. So we have pi squared EI in the X direction now, and we have KLX, right, squared. Well, why do I denote KLX? Okay. Well, the reason why I denote KLX is the fact that, in the real world, there's a lot of complexities. So, and a lot of different design considerations and constraints and design requirements to the fact that, we might not just have these two columns, okay, that span 35 feet and nothing touches these columns in that entire span. We might have something that frames in to this column, right? Might frame in on the side there, right? In such a way of like, well, if we look back all the way back at the beginning, right? The CET problem, right? This column, if we're looking at this column here, right? That column has a beam framing in on both sides, right? But in the back side, there's only one framing in, and the front side, there's not. Well, in some cases, the one framing in on the back side might not even be there, and we might just have these two columns that are essentially supporting this column from moving side to side, right, at that point, but not so much in and out of the page, right, if this column didn't exist, or this beam didn't exist, right? And so we want to make sure that the distance or the length over which that column buckles is the length over which is we consider with respect to the direction we are considering. So in this case, we want to make sure we use L sub x, because it's possible it might not be the same. So we have pi squared, 29,000 KSI times 144 inches to the fourth, right? That's I sub x, all over K, well, we know that's 1.0. The length is 35 feet. We don't have any intermittent supports. Well, as you can see, everything else is in inches, so I'm going to change this to inches. And it's going to look something like that. And when we calculate P critical in the X direction, we're going to get 233.6 kips. Wow, right? 230,000 pounds, okay? Fully loaded semi-truck, right? We've talked about this with rebar, 80,000 pounds driving down the highway. Well, if we had a channel that was made out of steel, it was only 12 inches tall, right? And if we look at the flange width of this 12-inch tall channel, right? Flange width, B sub F, it's 3.5 inches wide, right? So not a very big channel. Okay, it could be 35 feet tall, right? Literally 3 stories tall. And you could put nearly 3 of those semi-trailers sitting on top of it. Super incredible, right? Super incredible. I think it's fascinating. Okay, so if we start looking at the y direction, right? We will need to look at both directions. Y squared, EI, now of the y direction. And we have K Ly squared, okay? What does that equal? Well, pi squared, 29,000 times, now our I is a lot smaller, times 1.0 times 35 times 12 squared, okay? What do we get? Well, we get P critical in the y direction equals 7.22 kips, right? So now, right, and as you can see, and I think it's fairly intuitive, right? If we had one of these cross sections, right, if we were going to rotate about the x-axis, right, this cross section is pretty strong, right? It's got a lot of depth to it, as you guys calculated in mechanics class, right? You've got a lot of depth to it, so it will have a higher resistance to buckling about the x-axis as opposed to the y-axis, right? When we start rotating about the y-axis, right? It's a very, very thin member. So if we started to rotate that, right? It's just like if you took a ruler and in the flat direction you try and bend it, right? It doesn't have a lot of resistance, but if you flipped it 90 degrees and it's tall in your hands and you try bending it, there's a lot of resistance there, okay? So that's what that is what is highlighted. So that's why if we look at our capacity, we have way less capacity, okay, a factor of 30 almost, okay, here with respect to the capacity. So remember, our total capacity is 2 times the channel capacity. Well, if we started to load this up at starting with 0 kips and we incrementally increased it, right, we're going to hit 7.22 kips before 233 kips. And so we're going to say P critical total equals 2 times 7.22 kips, right? Or 14.4 kips. Still, pretty significant amount of weight, right? I mean, big 3/4 ton pickup, somewhere in that 4,000 to 6,000 pound range. So you can take 2 of those, sit them on essentially a pedestal that was 35 feet tall, and it's a single channel, right? I think that's incredible. It really lends itself to highlight the power of steel. All right. So that was part A. Well, part B says, well, now let's lattice these channels back to back. And maybe you're thinking already, right? That makes a lot of sense, right? As we mentioned, the resistance to rotation about the y-axis versus the x-axis, and how you would denote the x-axis as the strong axis, right? Because our moment of inertia is larger. And so in order to overcome some of the restrictions of, this reduced capacity of 7.22 kips, well, if we created a lattice framework that then made this cross-section work all together, right? If it worked all together, then it would increase our weak axis or our y-axis buckling and allow us to have higher capacity. So again, let's start by getting all of our information out there. 7.34 inches squared. We've got x bar equals 0.674 inches. I sub y 4.45 inches to the fourth. E equals 29,000. KSI, we've got I sub x equal to 144 inches to the fourth. We have length 35 feet, and K equals 1.0. All right, we have all of that information. I'm gonna get a drink of water. All right, part B says, if they're latticed back to back, now find the critical load. Well, we're not changing anything with respect to the x direction, right? We're going to ignore the lattice bars, add any stiffness, right, with respect to the rotation about the x-axis. But what they do is make the channels act integral with one another. So we need to find our new I sub y, right, of our composite section. Moment of inertia of our composite section. Well, from statics, as you know, right, the moment of inertia about a given coordinate, right, axis, is the moment of inertia about a reference axis plus the area of our cross section times the distance of that area, right, the centroid of that area to our new axis that we want to go to, right, parallel axis there. So distance equals, or D equals the distance between coordinates of interest. Right. So D, if we go back up there, right, originally our neutral axis or our centroidal axis of our channels was sitting right here, right? This would be X bar, Y bar. And if we go back to our cross section, right, they give us this big Y and big X. Well, that it means this is our centroid location of our channel. Well, now if we are integral with one another, our new location of our centroid is right here, right? Symmetrical. So now we're going here. So this distance that we're moving is d. Right? Well, we know that from the back of our channel to the back of the other channel is 6 inches. So if we were going to come up with that distance, d, we're going to say that that's 6 inches divided by 2 plus our centroidal location, or x bar. Well, we end up getting 3.674 inches. IY, well, now we get 2 times, right? We're doing this twice. We have 2 channels. We're going to move this one to the right, and we're going to move that one to the left. We're going to move it the same distance, so we can just multiply our parallel axis there by 2. So we have our moment of inertia about our centroidal axis of our individual channels, and we're going to add that to the area 34 inches squared times d, which is 3.674 squared. What do we get? We get 207 inches to the 4th. That is I sub y. Right? Well, knowing that the length of our columns, right, in reference to each of our rotational axes, right, which axis it's going to buckle over, right, whether it's x or y, are the same distance, right? This column's 35 feet in reference to both directions of buckling. Like I mentioned, in some cases, that might not be the case, right? We might have some support that comes into our column, like what's going to be in the homework, and we're going to assign. Right? It might be supporting that column in one direction so that the length in one direction is different than the length in the other direction. All right. But in this case, because they're the same length, if we look at our governing equation, right? Pi squared EI over KL squared. Well, K is the same and L is the same between both of our axes. E is the same and pi is the same with both of our axes. Really, it's this IY term that's driving the capacity, okay, of our column. So now that we have I sub y composite, we can really just compare, right? Put IX versus IY, okay, to see which one is more. Well, if you look at IX, if we have 2 columns, IX is now going to be twice, right? 144 or 288 inches to the 4th. Well, that's greater than 207 inches to the 4th. Well, what does that mean? Well, that means that I sub y still controls capacity. Right? It's the lower number, and if it's the lower number, it's in the numerator, and it's going to give us a lower capacity. Well, now we can finally go through and say, okay, P critical equals pi squared EI, right, KL squared. Well, so pi squared, 29,207, K 1.0, length 35 times 12 squared. We get 335.9 kips. Right. That is incredible. Right. So 1/3 of a million pounds by just putting some lattice formwork between these channels. Right. Incredible. And that would be the capacity of this. We don't multiply this by 2, right? Because we essentially calculated our moment of inertia based on both our channels, right? Acting compositely. Right? We did add our moment of inertia twice here, so we can make that comparison because we do have 2 independent channels working together in the x direction. Okay. That ends chapter 16, and we're going to jump to actually chapter 6 now. Okay, so that's all of columns. We're going to jump to chapter 6. Oh, sorry. Chapter 6, but note 7. Note 7 is all about torsion. all right? Torsion comes from a torque, right? So torque and moment are really synonymous, okay? They're just rotational forces, right? So torque, whoa, let me get rid of my highlights. Torque is a moment that tends to twist a member about its longitudinal axis. Okay. Well, what does that look like in the real world? That looks like a car's drive shaft, really. So, and this being an internal combustion engine, okay? So what do we have? Well, we have an internal combustion engine sitting at the front, okay? For those of you who don't know, I'm sure a lot of METs probably do. All right, so you have an internal combustion engine at the front, transmission attached to that engine that takes rotational power and converts it, okay, based on speed and power requirements to other components in the vehicle. All right, a lot of times if we just had a real world drive vehicle, okay, we need to transfer that rotational power, right, and speed of rotation to some sort of drivetrain, right, to drive you forward. That would be your axles. Okay, so it goes through a differential that changes the direction of that rotation into your forward motion, right, or reverse motion at your vehicle. Okay, so in this class, all right, so that's a real world example of a torsional member. Okay, we will cover torsion of shafts. And more specifically, okay, so these are some shafts, all right. In this case, we have a round shaft, okay, and a square shaft. Well, if you took a round shaft and you imposed upon it a torque, right, put it in torsion, torque is just a moment that twists a member about its longitudinal axis. So this would be our longitudinal axis. So we put a torque on that member. If it's round, okay, all these lines in this grid we had would continue to be straight lines, okay, right? Plane sections remain plane, right? So all of these remain straight with the world, right? We do have curvature, right, or rotation, and we'll talk about that here in a second. But a round shaft remains plane perpendicular to that. A square shaft, on the other hand, as you can see here, right, we get this, what we call warping going on, okay? So we are going to focus on, in this class, keep it simple. Principles are still there with square shafts. We just have to add some complexities to it, right? We're going to focus on circular shafts, and really we're going to be looking at solid and hollow. Circular shafts, okay? Well, as we've done with any of our forces, right? Stress, strain, things like that. We talk about the sign convention so that when we are doing free body diagrams to determine internal forces, which that's exactly what a torque is, right? It's an internal moment, internal force, okay? If we look at a 3D view, well, a torque is considered positive, all right, if it's outward from our surface. Well, that's very similar to an axially loaded member, all right? If we drew a free body diagram, a two-dimensional free body diagram, and if we took a section of this member and we looked at the end of it, okay, we would denote that torque, right? Torque 1 on one end, torque 2 on the other end, have to have our coordinates, right? If we added our coordinates, it would look something like this, right? Where we could sum the moments about the x-axis, right? That would be our x-axis. And that would also equal 0, right? Equilibrium still stands. And that'd mean that T1 minus T2, right? Those are our assumed directions equal to 0. Well, that means T1 must equal T2, right? That would be going through a free body diagram. As you can see, we denote those forces as double arrows or double headed arrows, right? We have double arrow vectors, okay? And that just denotes that it's a torque, all right? So that's our sign convention. Well, as we know with mechanics, right? If we apply forces create strain, right? Deformation. And so if we looked at our shaft and looked at the applied force on that shaft, okay, and we looked at a shaft that was fixed, say on a wall, and we applied a rotation to it, okay, and we wanted to twist it at the end, okay, so this was fixed. So that when we rotated, right, applied that torque T, we look at like a double arrowed vector, okay, and we pulled out that little sliver, right? If we looked at this little sliver and we pull that sliver out, right? Just some small little distance or puck, if you will, of that shaft is going to be a solid shaft, right? And we looked at one of those little squares, right? As you can tell, those squares elongate, right? And those squares again each have angles, right? Interior angles. Those interior angles we might call theta, and we know that those are not going to be equal to 90 degrees if we apply a force, because if we apply a force, we're going to get a strain, and we know that we're going to start out straight, and as we apply a load, we're going to essentially distort that square section. So again, if we look at that in more detail, okay, of that sliver, and we look at, right, this is the total, this outside circle, right? This is the outside circle or outside extents, right, of our sliver we just cut out, right? This is that outside surface, okay? Well, if we start by looking at rotation, right, the angle of rotation, call this the angle of rotation. And right, angle or angle of twist. It's positive. Whoops, doing here. It's positive following the right-hand rule, right? So if we curled our fingers in the direction of that angle of twist, right, made our thumb outward normal from the surface, it's going to be positive, right-hand rule. So in this case, we look at our sliver of our shaft, we applied a torque that was right to the right-hand rule gives us the direction of that vector, right? So if our torque is twisting counterclockwise on the end of that shaft, if we curl our fingers in that direction, our thumb points off to the right, well, that's where that vector direction goes, all right? And same goes for our angle of twist, right? So if we start at the origin, right, or the center line, or the longitudinal axis of our member, if we start at the center line, our change in our angle of twist equals 0, right? As you can see there, that angle of twist starts at 0 and it linearly increases, right? So we have this gamma, as we know, is shear strain from before. Whoops, shear strain, right? And it linearly increases as we move, right, from left to right on our shaft, right? From the fixed location, well, at the fixed location, it can't have any rotation. But as we move along the shaft out to our force T, right, we're going to have linear increase in strain. We're going to have a buildup in strain. Right? And like we've done in the past, right, we need to come up with some way of relating stress to strain. We would do the same thing with Hooke's law, where we have stress equals E epsilon, not E sigma, E epsilon, right? And our shear strain equals the change in angle of rotation over the change in distance, right? Delta X, right? And we know that our shear stress equals the shear modulus times the shear strain, right? That was our Hooke's law with respect to shear stress. Right? So as you can see, as we get out here, right, to the outer edge, as we get further and further out of our thing, of our shaft, right, we have the max rotation. Or twist at the outside face. Right? So if this was a pool noodle and you had someone hold on to one end of it, you held on to the other, and you rotated it with this torque T, right? That noodle would not rotate at the end that was being held fixed, right? But at your end, you're going to rotate the most, right? Rotate the most. And so we have this kind of linear increase in rotation, all right, as we go from the fixed support out to the applied load T. And if you looked at the center of the noodle, right, the center of the noodle isn't going to have any rotation, right? The very center of the noodle, it's at the origin. And that rotation is going to be maximum at the outer edge, okay? Let's look at what this means. Torsional shear stress. Well, if we look at torsional shear stress and we relate that back to strain, right, we have this Hooke's law relationship where we have the shear modulus, which is essentially the stiffness of a material, right, in shear. We have the Young's modulus, which is the stiffness in axial load, right? So it's the same thing where we have E epsilon equals sigma. Well, now we have tau equals G times gamma, okay? Well, if looking at that equation, if our strain increases, right, if gamma increases there, and more importantly, if it increases linearly like we saw here, right, we have this linear behavior, right, that our angle of rotation increases as we go along the length. Well, if that angle of rotation increases, well, our shear strain, right, the change in these angles of our square is also going to change. So they change linearly. If strain increases linearly with radius, so does stress. Right? So if we look at a cross section now, right? So we're going to look down on the end of this. Right, so we're looking this way. All right. At the end of this section, and now we have this angle of rotation, right? So we have this delta phi. All right, so we got this angle of rotation. Well, we know that that angle of rotation is proportional to or is equal to the shear strain. Well, if the shear strain is proportional to the shear stress, well, if our angle of rotation varies linearly from the center to the outside, well, so does our shear stress, right? So if we picked a point, right, this we might call it rho, and we call that rho the distance to a point from the center. Our shear stress at that point, okay, is tau p, which is going to be, right, if we look at this as a triangle, where it's maximum at our maximum radius, right, which would be C. This is our max radius. And it's minimum at the center at 0. The slope of that curve, right, is really going to be tau max over C, right, the rise over the run. And we're going to multiply that by the run, which is now rho, and that'll give us the value of our shear stress at some point, right, distance from the outside or the inside, right? We want to make some relationship between force and stress, right? We want to know if we have this torque applied to the end of this shaft, right? What stress is that going to result in? Okay. In mechanics, that's what we're always trying to do, right? We're going to figure out applied loads based on free body diagrams. Once we have those applied loads, we need to relate or figure out a way to get applied stresses so that we can relate that back to material properties. So we know a lot of things, don't we? Force equals stress times area. We know moment is force times some moment arm, right? Well, using that understanding, or if we want a force-stress relationship, as I mentioned, we want to relate torque, which is just a moment about the longitudinal axis. So we want to relate torque to shear stress, right? We're going to have materials that we're going to want to build our shafts out of. Those materials are going to have, yield stresses and ultimate stresses, which we're going to consider failure stresses depending on the use of these shafts. And then once we have these failure stresses, right, we can use factors of safety based on development of these loads, and then we can determine what an allowable stress would be, and we can continue to move forward, right? So if we start by looking at this idea of force is stress times area, okay? If we looked at a very, very small area, okay, I'm going to say it's a very small area, and it's oriented right there at a distance rho out from the center, okay? Well, that little small area, we're going to call it dA, is going to have some sort of stress, right? All of that stress that's sitting here is going to be acting on that area. Well, if all that stress is acting on that area, right, we know that force over area is stress. So stress times an area is force. And we can then develop, well, what's going on here with respect to this dF, right? So if we knew that relationship, looking at that small thing, we have dF equals tau p, right? Looking at some small stress at dA, right? If it's small enough, the variation of tau p is going to be small enough. We can just look at it as tau p. So this is our shear force. This is our stress at dA, and obviously that is dA, okay? Well, if we now know that there's a force acting at a distance rho from the center, if we were looking at the torque, right, or the moment, right, dm, that is acting, right, at that, due to that applied force, we would get rho dF, right, where this is our force. This is our arm, right, our moment arm. and we would get our moment, right, or torque. Well, if we plug these two together, right, we're going to get that dm equals rho tau p dA, right? That's just plugging in tau p dA for dF. From that, we get rho times rho tau max over c, right? That's what we just derived up above, times dA. Well, if we want the total torque, we need to integrate. I'm going to save you with some of this, but we want the total torque. We would sum up all of the forces, right, that are acting. All the forces that are acting. So there's this dF. Well, there's another dF here and here and here and here and here and everywhere along this whole thing, right, acting in our directions. And so if we were to integrate, which is essentially just taking the sum over the area of the moment, we would get tau max over c of the integral of rho squared dA, okay? Well, this little term here is what we would call the polar moment of inertia. J. So our force-stress relationship then becomes, right, if we were integrating the total torque, right, or integrating the moment, we would say our torque, T, now equals tau max, J, right, polar moment of inertia, over C, right? Or, we rearrange this, the maximum shear stress in our shaft, right, our circular shaft, is the torque times the maximum radius divided by the polar moment of inertia, right? So we have T equals torque. We have C equals max radius. We have tau max, which is just that, is the maximum shear stress. J equals polar moment of inertia. And similarly, right, if we pulled back out and we looked at, well, if we want to know, based on that tau max equation, if we want to know any torque or any stress, right, at a given radius, we could apply the torque, multiply it by a given radius divided by J, right? Just essentially the same thing. Instead of looking at the maximum radius, which would occur at our maximum, or a maximum stress, which occurs at our maximum radius, we can figure out the stress at any radius, right? Shear stress at any rho, which is radius. Okay, with that, I'm going to stop. There's a good place. We will pick this up on Wednesday, right? The day, because Monday is President's Day on the 21st. So I will see you on February 23rd. And yeah, talk soon. Don't forget, homework due dates. Check out D2L announcements. Also make sure that you don't miss the quizzes, okay? There's going to be a quiz due next week. Next week, as in there's a quiz available on the 16th through the 18th, okay? Make sure you separate some time there, an hour of your time to make that happen. Don't forget that we have a homework due on the 17th, okay? I'm going to issue another homework that's going to be due the week of the 23rd, and then also a quiz that would be due that week also. Also something to note and to consider is that the career fair is next week also, February 16th through the 18th. So make sure you give yourself some time to visit with them. Had some great conversations with Nucor Building Systems and Nucor Volcraft, which does open web steel joists. They're looking for all types of fabrication, engineering, project management, all of that stuff. So there's a lot of hungry employers out there. So this is a great time to be looking at internships and things like that. So anyway, good luck with that. Feel free to reach out with homework issues. We have Daruk, Arash, also Dr. Murray. While I'm gone, if you have anything, just email her. She said she is happy to help also.